The story begins not with telescopes or satellites, but with a pen and paper in 1916, just months after Albert Einstein published his field equations for general relativity. A German physicist named Karl Schwarzschild was solving those equations from the trenches of World War I. He was calculating the gravitational field around a perfectly spherical, non-rotating mass. What he discovered would haunt physicists for generations. Schwarzschild found something unexpected in the mathematics, a radius where the geometry of spacetime became so warped that even light, traveling at its constant cosmic speed limit, would be forced into a circular orbit. The radius was precisely 1.5 times the Schwarzschild radius, the boundary we now call the event horizon. For a black hole with the mass of our Sun, this photon sphere would exist just 4.4 kilometers from the center. For a supermassive black hole like Sagittarius A star at our galaxy's core, it extends to roughly 13 million kilometers. At first, this seemed like a mathematical oddity, a quirk of the equations with no real physical significance. But Schwarzschild understood something profound. If light could orbit at this radius, it meant that gravity had literally bent space-time into a closed loop. Not just curved it, closed it. The implications were staggering.
Imagine a place where light itself becomes trapped. Not absorbed, not reflected, trapped in an eternal orbit, circling the same point in space forever. This isn't science fiction, it's real. And it exists at the edge of every black hole in the universe. 3 kilometers above the event horizon of a stellar mass black hole, there's a boundary that defies everything we understand about light, time, and causality itself. Cross this threshold and photons, particles that have traveled freely through space since the Big Bang, suddenly find themselves imprisoned in perfect circles, unable to escape or fall inward. Scientists call it the photon sphere, and what happens there challenges the very foundations of physics. In this region, you could theoretically see the back of your own head. Time dilates to impossible extremes, and the laws of cause and effect begin to break down in ways that make quantum mechanics look straightforward. What if I told you that understanding this impossible boundary could unlock secrets about the nature of reality itself? That the photon sphere represents not just a mathematical curiosity, but a window into the fundamental structure of space-time. Today, we journey through evidence that challenges everything we thought we knew about light, gravity, and the fabric of the universe.
The story begins not with telescopes or satellites, but with a pen and paper in 1916, just months after Albert Einstein published his field equations for general relativity. A German physicist named Karl Schwarzschild was solving those equations from the trenches of World War I. He was calculating the gravitational field around a perfectly spherical, non-rotating mass. What he discovered would haunt physicists for generations. Schwarzschild found something unexpected in the mathematics, a radius where the geometry of spacetime became so warped that even light, traveling at its constant cosmic speed limit, would be forced into a circular orbit. The radius was precisely 1.5 times the Schwarzschild radius, the boundary we now call the event horizon. For a black hole with the mass of our Sun, this photon sphere would exist just 4.4 kilometers from the center. For a supermassive black hole like Sagittarius A star at our galaxy's core, it extends to roughly 13 million kilometers. At first, this seemed like a mathematical oddity, a quirk of the equations with no real physical significance. But Schwarzschild understood something profound. If light could orbit at this radius, it meant that gravity had literally bent space-time into a closed loop. Not just curved it, closed it. The implications were staggering.
Think about what this means. Light is the universe's ultimate messenger. Since the Big Bang, photons have traveled freely through space, carrying information across billions of light years. They illuminate our world. They enable sight, communication, and every astronomical observation we've ever made. Yet here, at this specific radius around a black hole, photons lose their freedom entirely. Here's the critical detail. The photon sphere isn't stable. A photon orbiting at exactly this radius exists in what physicists call an unstable equilibrium. The slightest perturbation, the tiniest gravitational wave, a passing particle, even quantum fluctuations will cause it to either spiral into the black hole or escape to infinity. It's like balancing a pencil on its tip. Theoretically possible, but practically impossible to maintain. This instability reveals something crucial. The photon sphere represents a boundary condition in space-time itself. It's the point where the curvature of space becomes so extreme that light's natural forward motion gets redirected into a perfect circle.
But here's where it gets strange. In the 1960s, physicists Brandon Carter and James Bardeen expanded on Schwarzschild's work studying rotating black holes described by the Kerr metric. They discovered that rotation adds layers of complexity to the photon sphere that nobody anticipated. For a rotating black hole, there aren't one, but two photon spheres, or more precisely, a photon surface with different properties depending on whether light orbits in the same direction as the black hole's rotation or against it. Light orbiting with the black hole's rotation, prograde orbits, can exist at a radius farther from the event horizon. Light orbiting against the rotation, retrograde orbits, must be closer in. The difference can be substantial. For a maximally rotating black hole, the prograde photon sphere exists at about 4 times the gravitational radius, while the retrograde sphere sits at just 1.5 times that radius. This asymmetry reveals something profound about how rotating mass drags spacetime itself into motion, a phenomenon called frame dragging. Let me give you an analogy that captures the strangeness of this region. Imagine you're driving on a circular track. Normally, if you turn the steering wheel left, you turn left. Turn it right, you turn right. Your motion follows your intentions. But on this track, the road itself is moving, rotating beneath you. If you try to drive against the rotation, you have to turn harder, fight more resistance, stay closer to the center to maintain your circle. If you drive with the rotation, the road helps you, allows you to maintain a wider circle with less effort. The photon sphere works similarly, except it's not the road moving, it's space-time itself. The black hole's rotation literally drags the fabric of space around it like a whirlpool, and photons must navigate this rotating geometry. But the evidence forces us to confront an uncomfortable possibility. What if the photon sphere isn't just an interesting boundary, but a fundamental feature of how information, causality, and reality itself behave at the edge of extreme gravity?
For decades, the photon sphere remained purely theoretical, a mathematical prediction with no observational confirmation. How do you observe something that exists for only the briefest instant, around objects we couldn't even photograph? The breakthrough came in April 2019. The Event Horizon Telescope collaboration released the first image of a black hole, the supermassive giant at the center of galaxy M87, 55 million light-years away. What captured global attention was the bright ring surrounding the dark central shadow. That ring isn't the photon sphere itself, but it's intimately connected to it. Scientists discovered that the bright ring sits at approximately 2.6 times the Schwarzschild radius. The photon sphere, by comparison, exists at 1.5 times that radius. The ring represents photons that barely escape the photon sphere's gravitational grasp, light that skimmed just outside this boundary before reaching our telescopes. The radius of that bright ring provided the first direct observational evidence that the photon sphere's mathematics matches physical reality.
But this represents just one piece of a much larger puzzle.
In 2020, researchers at Radboud University in the Netherlands analyzed the M87 image with unprecedented precision. They identified multiple nested rings in the emission pattern, what they called photon subrings. These subrings represent light that has orbited the black hole multiple times before escaping. Each successive ring corresponds to photons that completed one more orbit around the photon sphere before breaking free. The first subring comes from photons that orbited once, the second from those that orbited twice, and so on. The team calculated that theoretically, infinite subrings should exist, each fainter and more tightly packed than the last. They detected evidence for at least 3 distinct subrings in the data. This discovery confirms something remarkable. Photons really do orbit black holes, exactly as the mathematics predicted. The photon sphere isn't just a theoretical boundary. It's a real region where light physically circles before either escaping or being captured.
The most remarkable discovery involves gravitational lensing. When light from a distant source passes near the photon sphere, the extreme curvature of spacetime creates multiple images of the same object. But these aren't ordinary lensing effects. The photon sphere creates what physicists call relativistic images. In 2021, researchers at Harvard-Smithsonian Center for Astrophysics published calculations showing that a star orbiting close to a black hole would appear multiple times in an observer's field of view. Each image corresponds to light that took a different path, some direct, some having orbited the black hole once, twice, or more times before reaching the observer. The team calculated that for Sagittarius A star, our galaxy's central black hole, certain orbital configurations would create dozens of visible images of the same star. Each image would show the star at a different point in its orbit because the light took different amounts of time to reach us. This means an observer at the right position could watch the entire orbital history of a star simultaneously, past, present, and multiple possible futures, all visible at once.
The evidence extends beyond black holes into the realm of neutron stars. In 2018, astrophysicists at the University of Amsterdam discovered that ultra-compact neutron stars, those just above the mass threshold for collapsing into black holes, can also possess photon spheres. Their calculations showed that a neutron star with a radius less than 1.5 times its Schwarzschild radius would trap light in the same way black holes do. This discovery revealed that the photon sphere isn't unique to black holes, but represents a universal phenomenon of extreme gravity. NASA's NICER telescope, mounted on the International Space Station, has been mapping the surfaces of neutron stars using X-ray pulses. The team discovered that light emitted from the far side of certain neutron stars curves around the entire star and becomes visible to us, light that should be hidden by the star's bulk. This gravitational lensing effect indicates these neutron stars sit right at the edge of having photon spheres. A slightly higher mass or smaller radius, and they would cross that threshold.
Now we venture into stranger territory. In 2022, theoretical physicists at the Max Planck Institute published findings that seem to contradict established physics. They discovered that quantum effects near the photon sphere could theoretically allow information to escape from regions where classical physics says escape is impossible. The calculation involves Hawking radiation, the quantum process by which black holes slowly evaporate. The team found that quantum fluctuations at the photon sphere could create pairs of entangled photons, with one falling into the black hole and one escaping to infinity. Here's the unsettling part. These entangled photons could theoretically carry information about the black hole's interior to the outside universe. This challenges the black hole information paradox, the unresolved question of whether information that falls into a black hole is destroyed or preserved. The photon sphere might be the mechanism by which quantum information escapes. Preserved through entanglement,
even as one half of the pair crosses the event horizon.
The most disturbing evidence comes from computer simulations of light behavior near rotating black holes. In 2020, researchers at Princeton University created detailed ray tracing simulations, showing what an observer would see while crossing the photon sphere. The results were profoundly disorienting. As you approach the photon sphere from outside, your forward view compresses. Stars directly ahead appear in an ever-shrinking circle. Meanwhile, your rear view expands until it fills your entire peripheral vision. You can see behind yourself without turning around. At the photon sphere itself, this effect becomes extreme. Looking forward, you see the entire universe compressed into a tiny point of light directly ahead. Looking to the side in the direction of your orbit, you see the back of your own head, illuminated by light that has traveled around the photon sphere to reach your eyes. The simulations showed that time dilation at the photon sphere becomes so extreme that an observer there would perceive the outside universe evolving at tremendous speed. Stars would be born and die in what feels like seconds. Galaxies would collide and merge in minutes.
Recent observations reveal patterns that shouldn't exist. In 2023, astronomers using the Event Horizon Telescope detected quasi-periodic oscillations in the brightness of the ring around M87's black hole. These oscillations occur at specific frequencies that match theoretical predictions for photons orbiting at the photon sphere. The discovery suggests that the accretion disk's hot plasma sends pulses of light that get temporarily trapped in the photon sphere before escaping. Each pulse orbits multiple times, creating an echo effect like sound bouncing around a canyon, but with light orbiting a black hole. These oscillations provide a direct probe of the photon sphere's properties. By measuring the frequency and damping rate of these echoes, scientists can map the spacetime geometry in this region with unprecedented precision. The data revealed something unexpected. The oscillations show slight irregularities that can't be explained by standard general relativity alone. The deviations are small, within margins of error, but they hint that quantum gravitational effects might become important at the photon sphere, effects our current theories can't fully describe. The evidence extends beyond physics into the realm of information theory. Physicists have calculated that the photon sphere acts as an information boundary, a surface where the entropy of the spacetime region changes discontinuously. This connects to the holographic principle, the idea that all the information contained in a volume of space can be encoded on its boundary. The photon sphere might represent a holographic screen where three-dimensional information about the black hole's interior gets encoded in a two-dimensional surface. This could mean that everything happening inside the photon sphere, including at the event horizon and potentially inside the black hole itself, is somehow stored as information at this boundary. If true, this transforms our understanding of what a black hole is. Not a region of space, but an encoding of information on a spherical surface. The scientific theory that ties everything together is general relativity's prediction of unstable circular photon orbits combined with quantum field theory in curved spacetime. According to general relativity, the photon sphere emerges naturally from the geodesic equations, the mathematical description of how particles move through curved spacetime. A photon following a null geodesic at exactly the right radius will find itself in a circular orbit because the curvature of space perfectly balances the photon's natural tendency to move in straight lines. But general relativity also tells us this orbit is unstable. The mathematical second derivative of the effective potential for photons is negative at the photon sphere. This means any small perturbation causes exponential divergence. The orbit quickly collapses or expands. Leading physicists have competing interpretations of what this instability means. Kip Thorne at Caltech has argued that the photon sphere's instability makes it a caustic, a focusing point where light rays converge. He suggests this is why the photon sphere creates such dramatic lensing effects.
Light doesn't actually orbit there for any significant time, but passes through, getting bent by the extreme curvature. In contrast, Roger Penrose proposed that the photon sphere represents a boundary of absolute future for light rays. Once light crosses inward past this boundary, its future is determined. It must fall into the black hole. The photon sphere marks the point of no return for light, just as the event horizon marks the point of no return for everything else. A third perspective, championed by researchers at the Perimeter Institute, views the photon sphere through the lens of black hole thermodynamics. They argue it represents the boundary where the black hole's temperature, as measured by an observer at that radius, diverges to infinity. This connects the photon sphere to the fundamental physics of black hole evaporation.
This forces us to reconsider fundamental assumptions about spacetime itself. The existence of the photon sphere demonstrates that spacetime can fold back on itself in ways we don't encounter in everyday life. The circular light orbits represent closed paths through space, light that returns to where it started without ever turning around. This has profound implications for causality. In special relativity, light cones define what events can influence what other events. Cause must precede effect, and influences propagate at the speed of light. But at the photon sphere, light cones tilt so extremely that they begin to close back on themselves. Theoretically, this creates the possibility of closed time-like curves, paths through space-time that return to their starting point in both space and time. Whether such paths actually exist and what they would mean for the nature of time remains one of physics' deepest mysteries. The photon sphere might be telling us that time itself isn't as fundamental as we thought. That in regions of extreme gravity, the distinction between past, present, and future breaks down in ways that challenge our basic intuitions about reality. Ongoing research is pushing our understanding into new territory. The Event Horizon Telescope collaboration is working on next-generation imaging that will resolve the photon subrings in unprecedented detail. Their goal for the next decade is to image black holes with resolution fine enough to see individual orbits of light, to literally watch photons circle the photon sphere. This will provide the most stringent test yet of general relativity in the strong field regime. Any deviation from Einstein's predictions would point toward new physics, potentially quantum gravity effects that current theories can't describe. NASA's upcoming LISA mission, scheduled for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers. These waves will carry information about the photon spheres of the merging black holes, allowing scientists to map their properties indirectly through gravitational radiation.
Recent breakthroughs suggest we may be able to probe the photon sphere using quantum entanglement. In 2023, theorists at MIT proposed an experiment using entangled photon pairs near a black hole. One photon would be sent toward the photon sphere while its entangled partner remains far away. By measuring correlations between the two photons, researchers could potentially extract information about space-time geometry at the photon sphere without directly observing it. This connects to the developing field of quantum sensing with gravity. The idea is to use quantum correlations, entanglement, and superposition as probes of gravitational fields. The photon sphere, with its extreme curvature and unique light-trapping properties, represents an ideal laboratory for such experiments. Several research groups are working on ways to create analog photon spheres in laboratory settings. By using specially designed optical materials with extreme refractive indices or acoustic analogs in flowing fluids, they hope to simulate photon sphere physics in controlled environments. What technologies might help solve remaining mysteries? Next-generation radio telescope arrays, including the Square Kilometre Array being built in South Africa and Australia, will provide unprecedented sensitivity to emissions from around black holes. These arrays will detect fainter signals and resolve finer structures than ever before.
Quantum sensors using atomic interferometry could potentially detect the subtle frame-dragging effects that rotate the photon sphere around spinning black holes. Such measurements would provide direct evidence for space-time rotation, confirmation that mass really does drag space itself into motion. The photon sphere could also become a tool for astronomy. Some researchers propose using black holes as gravitational telescopes, exploiting the extreme lensing around the photon sphere. The magnification could be enormous, millions or billions of times, potentially allowing us to see individual stars in distant galaxies or even planets around nearby stars with unprecedented detail.
In 1974, Stephen Hawking published a paper that shocked physicists worldwide. By carefully analyzing quantum field theory near an event horizon, he discovered that black holes aren't perfectly black. They emit radiation. The mechanism is subtle and beautiful. Quantum mechanics permits particle-antiparticle pairs to spontaneously appear from vacuum fluctuations throughout space. Normally, these virtual particles annihilate each other almost instantly. But near the event horizon, something remarkable happens. If a particle pair forms right at the boundary, one particle might fall into the black hole while its partner escapes. To an outside observer, the black hole appears to emit a particle. The energy for this particle comes from the black hole's mass, meaning the black hole slowly evaporates. The temperature of this Hawking radiation is inversely proportional to the black hole's mass. For a solar mass black hole, the temperature is 60 billionths of a Kelvin, far colder than the cosmic microwave background radiation. Such black holes absorb more energy than they emit and actually grow. But smaller black holes are hotter. A black hole with the mass of Mount Everest would glow at room temperature. A black hole with an asteroid's mass would shine brilliantly and explode within seconds. The implications are staggering. Black holes evaporate completely given enough time. A solar mass black hole would take 10 to the 64th power years to evaporate, vastly longer than the current age of the universe. A supermassive black hole, like M87's, would persist for 10 to the 100th power years. But eventually, inevitably, every black hole will radiate away to nothing, leaving only faint photons scattered across an expanding void.
The information paradox. Hawking radiation created a crisis in theoretical physics. The radiation appears to be purely thermal, completely random, carrying no information about what fell into the black hole. If a black hole evaporates completely, what happens to all the information about every particle, every atom, every structure that crossed the event horizon? According to quantum mechanics, information cannot be destroyed. The quantum state of any system must evolve deterministically. You can scramble information, encrypt it, spread it out, but fundamentally it must be preserved. This principle underlies all of quantum theory. But Hawking's calculations suggest black holes violate this principle. Information falls in, the black hole evaporates, and the information is gone, erased from the universe permanently. This isn't just a technical problem. If information can be destroyed, then quantum mechanics is wrong at a fundamental level. If information cannot be destroyed, then either Hawking's calculation is wrong, or general relativity fails at the event horizon, or our understanding of space-time itself requires revision. Physicists have proposed numerous resolutions. Perhaps information escapes encoded in subtle correlations between early and late Hawking radiation, correlations so complex they're effectively impossible to detect but technically present. Perhaps black holes connect to other universes through wormholes, and information isn't destroyed but transferred elsewhere. The most radical proposal suggests space-time itself is emergent, constructed from quantum entanglement in ways we don't fully understand. Black holes, by creating and destroying entanglement, might reveal that space and time aren't fundamental, but arise from deeper quantum information structures. Firewall or smooth horizon? In 2012, 4 physicists at UC Santa Barbara published a paper that ignited fierce debate. They argued that preserving quantum mechanics might require abandoning general relativity's prediction of a smooth event horizon. Their reasoning? If information must be preserved, then late Hawking radiation must be quantum entangled with early Hawking radiation. But quantum mechanics forbids a particle from being maximally entangled with two different systems simultaneously. The particle in the Hawking radiation cannot be entangled both with its partner that fell into the black hole and with previously emitted radiation. Something must give. The AMPS firewall hypothesis suggests that maintaining quantum mechanics requires the event horizon to be a region of extreme energy density, a firewall that would incinerate anything crossing it. This directly contradicts general relativity's equivalence principle, which states that freely falling observers should experience nothing special at the event horizon. The firewall would be very noticeable. It would vaporize you instantly. Other physicists strongly dispute this conclusion. Some argue the entanglement calculations contain subtle errors. Others suggest black hole complementarity, that the information is simultaneously both inside and outside the black hole, depending on the observer's reference frame, with no contradiction because no single observer can verify both perspectives. The debate continues. It represents physics at its most fundamental. Two bedrock theories, quantum mechanics and general relativity, apparently producing contradictory predictions. One or both must be incomplete. The evidence extends beyond theoretical calculations into observable signatures we might detect.
On September 14, 2015, at 09:50:45 UTC, gravitational waves from two colliding black holes swept through Earth. The Laser Interferometer Gravitational Wave Observatory detected them, ripples in spacetime itself, compressing and stretching the fabric of the universe by 1 part in 10 to the 21st power. The signal lasted less than a second, but encoded in that brief chirp was complete information about an cataclysmic event. Two black holes, 36 and 29 solar masses, had spiraled together over billions of years. In their final moments, they orbited each other hundreds of times per second before merging. 3 solar masses, equivalent to the energy in 10 to the 47th power nuclear bombs, were converted to gravitational waves in a fraction of a second. The peak power output of this merger briefly exceeded the combined light output of every star in the observable universe. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers. Each one reveals information about black hole populations, formation mechanisms, and the properties of extreme space-time. Some mergers show surprising features. GW 1905-21 involved an 85 solar mass black hole, a mass that shouldn't exist according to stellar evolution models. Stars massive enough to produce such black holes should explode completely, leaving nothing behind. Either our models are wrong, or this black hole formed through the merger of smaller black holes. Other observations revealed black holes with surprisingly low spin. If black holes grow through accretion, steadily feeding on surrounding matter, they should spin up to near maximum rotation. The discovery of slowly rotating black holes suggests different formation pathways, perhaps direct collapse, or mergers with specific orbital configurations.
We began by staring into the shadow of a black hole, a photograph that captured humanity's first glimpse of an event horizon. That image represented more than astronomical achievement. It marked a moment when we confirmed that the most extreme predictions of Einstein's theory match reality, that the universe contains regions where our everyday intuitions about space and time completely fail. Through our journey, we've traced evidence from dying stars to colliding black holes, from Hawking radiation to holographic principles, from gravitational echoes to the information paradox. Each piece of evidence reveals that black holes aren't just cosmic vacuum cleaners, indiscriminately devouring matter. They're laboratories where nature tests the limits of physics, where quantum mechanics and gravity engage in battle, where the structure of reality itself becomes uncertain. We've learned that event horizons are boundaries between comprehensible physics and something beyond our current mathematics. We've seen how black holes might encode information holographically, might connect to other universes, might be the offspring and parents of cosmos. We've confronted the possibility that space-time itself emerges from quantum foundations we don't yet understand. The current scientific consensus holds that black holes exist as general relativity describes them, that they emit Hawking radiation and slowly evaporate, and that somehow, through mechanisms still debated, information is preserved even if we can't yet calculate how. The consensus acknowledges deep mysteries remaining: the nature of singularities, the resolution of the information paradox, the quantum structure of event horizons. But certainty isn't the goal. Understanding is. Every answer spawns new questions. What is the quantum nature of spacetime? Can information truly disappear? Are we living in a holographic projection? Does the multiverse exist? Black holes remind us that the universe is not required to make sense to us. It exists according to its own laws, following mathematics that sometimes leads to conclusions that seem impossible, boundaries that seem paradoxical, futures that seem unimaginable. Yet, we persist in trying to understand. We build telescopes the size of Earth. We detect ripples in space-time from collisions billions of years ago. We propose theories of quantum gravity and test them against observation. We photograph shadows cast by regions from which light cannot escape. This is humanity's deepest gift, the ability to look at the universe's most mysterious phenomena and ask, why? To push against the boundaries of knowledge, to chase understanding to the event horizon and beyond. The universe is vast. The mysteries are endless. The journey continues.
In the far future, so far that current timescales become meaningless, black holes will dominate the universe. Stars will burn out. Galaxies will evaporate. Matter will decay. Eventually, only black holes will remain, scattered through an expanding void. And then, slowly, the black holes themselves will evaporate through Hawking radiation. A solar mass black hole will take 10 to the 67 years to evaporate. A supermassive black hole like M87's will persist for 10 to the 98 years. But eventually, inevitably, they will radiate away to nothing. What remains? A cold, dark universe filled with photons redshifted to wavelengths larger than the observable universe itself. Occasional electron-positron pairs separated by distances vaster than our current cosmic horizon. This is the heat death, maximum entropy, minimum useful energy, the end of complexity and structure. But even this might not be the end. Some calculations suggest quantum fluctuations could spontaneously create new universes in the far future. Empty space itself might be metastable, capable of decaying to a lower energy state through quantum tunneling, releasing energy to create a new Big Bang. Black holes, having played their role in the old universe, might seed new ones. The most disturbing speculation involves vacuum decay. If our universe exists in a false vacuum, a metastable energy state, then quantum tunneling could trigger a phase transition, a bubble of true vacuum expanding at light speed, destroying everything in its path and replacing our physics with something utterly different. Black holes might accelerate this process, or they might stabilize the vacuum. We don't know. What we do know is that black holes represent endpoints, places where matter concentrates, energy dissipates, and information meets its ultimate test. They are the universe's way of pushing physical laws to their breaking point, revealing the cracks in our understanding. They show us that reality is stranger, deeper, and more mysterious than our ancestors ever imagined. At the event horizon, where time stops and space tears, the universe whispers secrets about its own nature, secrets we're only beginning to decode.
Black holes force us to confront the question, what is space-time? In our everyday experience, space and time seem fundamental, the stage on which events unfold.
But general relativity revealed they're dynamic, flexible, curved by mass and energy. Black holes take this to the extreme. At the event horizon, something remarkable happens to the concepts of space and time. The mathematical roles of space and time actually swap. Inside the horizon, the radial direction toward the singularity becomes time-like rather than space-like. Moving toward the singularity isn't a choice. It's as inevitable as moving forward in time. The future points inward. This suggests space-time isn't fundamental at all. Physicists studying quantum gravity increasingly believe that space and time emerge from something more basic. Quantum information, entanglement networks, geometric structures we don't yet understand. Black holes, with their holographic encoding of information and their violent mixing of quantum mechanics and gravity, offer clues to this deeper reality. If space-time is emergent, then asking what happens at the singularity is like asking what happens when you zoom into a digital photograph until you see individual pixels. The question assumes a continuous structure that doesn't exist at that scale. The singularity might not be a physical place at all, but rather a signpost showing where our description breaks down, where the emergent structure of space-time loses coherence.
There exists a place in the universe where time slows to a stop, where light, the fastest thing in the cosmos, becomes trapped forever, where all matter compresses into a point of infinite density, tearing the very fabric of space-time apart. This isn't science fiction. These are black holes. At the center of our Milky Way galaxy lurks a monster. A black hole with the mass of 4 million suns. Every 16 minutes, a star named S2 whips around this invisible giant at 5,000 kilometers per second, nearly 2% the speed of light. We've watched this star for over 20 years, mapping the choreography of its orbit to understand the gravitational abyss holding it captive. But here's what truly disturbs. Every single second, somewhere in the universe, a new black hole is born. A massive star exhausts its fuel and collapses, creating a tear in space-time. In the time it takes you to watch this documentary, approximately 3,600 new black holes will come into existence. And with each birth, physics confronts a paradox that threatens to shatter our understanding of reality itself. Today, we descend into the darkest depths of the cosmos, where the laws of nature are pushed to their absolute breaking point.
Some physicists speculate about civilizations advanced enough to exploit black hole physics. A sufficiently advanced civilization could use the Penrose process to extract energy from a rotating black hole, dropping material into the ergosphere, the region outside the event horizon where space-time is dragged around by the black hole's spin, and recovering more energy than you put in by carefully choreographed trajectories. The maximum efficiency of this extraction is staggering. Up to 29% of the black hole's rest mass could theoretically be converted to useful energy for a maximally spinning black hole. This far exceeds nuclear fusion, which converts less than 1% of rest mass to energy. A civilization could power itself for billions of years by carefully feeding a supermassive black hole and harvesting the energy from its spin. Freeman Dyson proposed that advanced civilizations might build structures around black holes, black hole engines that would be detectable as unusual infrared sources, warm objects where no star exists. SETI researchers have suggested looking for such signatures as evidence of Kardashev Type II civilizations, those capable of harnessing the energy output of their entire galaxy. Even more speculative, if traversable wormholes can exist, a possibility suggested by certain solutions to Einstein's equations involving exotic matter with negative energy density, black holes might become gateways rather than dead ends. Civilizations capable of stabilizing wormholes could use them for faster-than-light travel through space-time shortcuts. These remain theoretical curiosities. No evidence suggests such engineering is possible with known physics, but black holes represent the most energy-dense objects in the universe. Any civilization seeking to master energy at cosmic scales would have to grapple with them. The most profound implications emerge when we consider what black holes reveal about reality's deepest structure.
In 2016, Stephen Hawking proposed a potential resolution to the information paradox. He suggested that information isn't stored inside the black hole at all, but rather in soft hair, low-energy quantum fields at the event horizon that record the quantum state of infalling matter. Other physicists pursued different approaches. Researchers at the California Institute of Technology calculated that Hawking radiation might be more complex than originally thought. Subtle quantum correlations between early and late radiation could encode information about everything that fell in. The information emerges gradually, scrambled almost beyond recognition, but technically preserved. The most radical proposal suggests we need to revise our concept of space-time itself at the quantum level. If space-time is emergent, constructed from more fundamental quantum information, then the smooth event horizon of general relativity might be an approximation that breaks down when examined microscopically. At the Planck scale, 10 to the minus 35 meters, space-time might be granular, foamy, fundamentally quantum. String theory offers another perspective. In string theory's framework, black holes are collections of fundamental strings wrapped and vibrating in specific patterns. The information in any object falling into the black hole gets encoded in changes to how these strings are configured. Nothing is truly lost, it's transformed into the black hole's internal quantum state. These competing theories make different predictions about subtle effects, the exact spectrum of Hawking radiation, the gravitational wave echoes from black hole mergers, the microscopic structure of event horizons. Future observations might distinguish between them, revealing which path toward quantum gravity is correct.
The Event Horizon Telescope continues to refine its observations. In 2022, the collaboration released an image of Sagittarius A star, the supermassive black hole at our galaxy's center. This black hole proved far more challenging to image than M87's. Matter orbits Sagittarius A star in just minutes rather than weeks, meaning the accretion disk changes appearance faster than the observation time required to capture an image. But those rapid changes contain information. By observing how the accretion disk flickers and evolves, astronomers can test predictions about turbulence, magnetic fields, and matter flow near the event horizon. Upcoming observations aim to capture video of the black hole's immediate environment, watching matter spiral inward toward its doom in real time. New radio telescopes joining the array will improve resolution further. The eventual addition of space-based radio telescopes could extend the baseline beyond Earth's diameter, potentially resolving structure at the photon sphere, the innermost stable orbit for light around a black hole, where photons circle the event horizon in perpetual orbits before eventually escaping or falling in. Recent breakthroughs suggest even more powerful probes. The Laser Interferometer Space Antenna, planned for launch in the 2030s, will detect gravitational waves from merging supermassive black holes billions of light years away. These waves will encode precise information about the black hole's masses, spins, and the warped spacetime around them during merger. Each new observation tests general relativity in increasingly extreme conditions. So far, Einstein's century-old theory passes every test, but physicists expect that eventually, at small enough scales or extreme enough conditions, deviations will appear, signals of quantum gravity, the theory that must ultimately replace general relativity at the event horizon. At the center of every black hole, Einstein's equations predict a singularity, a point where space-time curvature becomes infinite, where density becomes infinite, where our mathematics produces meaningless results. This represents physics breaking down completely. Roger Penrose proved in the 1960s that singularities are inevitable inside black holes. Once an event horizon forms, he showed mathematically, nothing can prevent the complete gravitational collapse of all matter within it. The singularity isn't something that might happen, it must happen according to general relativity. But what kind of singularity? For a 9-rotating black hole, the singularity is a point, zero-dimensional, infinitely dense. For a rotating black hole, which all real black holes are, the singularity becomes a ring, a circle of infinite density within the event horizon. The mathematics suggests that you could, in principle, pass through this ring without hitting the singularity itself. Where would you go? The equations permit bizarre solutions. Passing through a rotating black hole's ring singularity might connect to a white hole, a time-reverse black hole that ejects matter rather than absorbing it, or to another universe entirely, or to a different region of our own universe, creating a wormhole through spacetime. Physicists believe these exotic solutions are mathematical artifacts. Real black holes probably don't contain traversable wormholes to other universes. Quantum effects near the singularity, currently beyond our ability to calculate, likely change the picture dramatically. But we don't know. The physics of singularities remains one of the deepest unsolved problems in theoretical physics. Kip Thorne at Caltech has argued that nature abhors naked singularities, singularities not hidden behind event horizons. The cosmic censorship hypothesis suggests that singularities always form enclosed by event horizons, preventing them from affecting the outside universe. But some exotic scenarios, colliding black holes, rapidly spinning black holes, or quantum effects, might violate cosmic censorship. Recent computer simulations have found rare conditions where naked singularities might briefly form, visible to the outside universe. What happens if you could observe a naked singularity directly? Nobody knows. It would be a region where causality itself breaks down, where effects could precede causes, where the normal rules of physics cease to operate. Some theorists suggest naked singularities are cosmic censorship's ultimate safeguard. Nature renders them invisible by making it impossible for signals from them to escape coherently. In 1993, physicist Gerard 't Hooft proposed something extraordinary based on studying black hole thermodynamics. He suggested that the information content of any volume of space can be encoded on its boundary, like a hologram. This idea, refined by Leonard Susskind, became known as the holographic principle. Black holes provided the key insight. Jacob Bekenstein had calculated in the 1970s that a black hole's entropy, a measure of information content, is proportional to the area of its event horizon, not its volume. This seems strange. Most systems have entropy proportional to volume. But black holes are different. Their information capacity scales with surface area. This forces us to reconsider fundamental assumptions about three-dimensional space. Any region is determined by the area of its boundary, then perhaps the three-dimensional universe we experience is actually a projection, a holographic image of information encoded on a two-dimensional surface. String theorists at Princeton extended this idea, proposing that our entire universe might be a hologram projected from its cosmological boundary. Black hole event horizons became models for understanding this deeper reality. The information that appears lost when matter crosses the horizon might actually be encoded in the microscopic quantum structure of the boundary itself. Leading physicists like Juan Maldacena at the Institute for Advanced Study developed mathematical frameworks showing how gravity in three-dimensional space can be exactly equivalent to quantum field theory on a two-dimensional boundary. Black holes became laboratories for testing these ideas, the only place in nature where the connection between gravity and quantum mechanics becomes unavoidable. The most disturbing theoretical prediction about event horizons emerged from calculations by physicists studying the information paradox. In 2012, researchers at the University of California, Santa Barbara proposed something radical. What if the event horizon isn't smooth and empty as general relativity suggests? What if quantum effects create a firewall at the boundary, a region of such intense energy that anything crossing it would be instantly incinerated? The argument goes like this. If information must be preserved, then the quantum state of Hawking radiation must be entangled with the information still inside the black hole. But quantum mechanics forbids a particle from being maximally entangled with two different systems simultaneously. Something has to give. The firewall hypothesis suggests that maintaining information conservation requires breaking the smooth structure of spacetime at the horizon, replacing it with a barrier of extreme energy. This idea challenged general relativity's equivalence principle, the foundation of Einstein's theory, which states that freely falling observers shouldn't notice anything special when crossing the event horizon. The firewall would very much be noticeable. It would destroy anything that encountered it. Other physicists proposed alternatives. Perhaps information escapes through subtle correlations in the Hawking radiation, or perhaps black holes are connected to new universes through their singularities, or perhaps our understanding of space-time itself must be revised at the quantum level. The most remarkable discovery involves recent calculations suggesting that black holes might be vast quantum computers encoding information about everything that ever fell in across the microscopic structure of their event horizons. Every particle, every photon that crosses the boundary might leave an imprint, a holographic record of its quantum state distributed across the horizon's surface. The evidence extends beyond astronomical observations into the realm of fundamental physics, and it suggests that reality itself works differently than we imagined.
In 2015, the Laser Interferometer Gravitational Wave Observatory detected ripples in spacetime itself, gravitational waves generated by two colliding black holes. The signal, designated GW150914, matched predictions from general relativity with extraordinary precision. Two black holes, 36 and 29 solar masses respectively, had spiraled together and merged, releasing 3 solar masses worth of energy as gravitational waves in a fraction of a second. But some physicists noticed something peculiar in the data. After the main signal, the chirp of the merger and the ring down as the final black hole settled into stability, there appeared to be faint, additional oscillations. These echoes arrived at regular intervals, as if the gravitational waves had bounced off something near the event horizon and escaped in pulses. According to general relativity's standard predictions, such echoes shouldn't exist. The event horizon is a perfectly absorbing boundary. Waves falling in don't bounce back. But some quantum theories of gravity predict the event horizon might have structure, a quantum atmosphere or firewall at the boundary that could partially reflect gravitational waves. Subsequent analyses have been controversial. Some research groups claim to detect these echoes in multiple black hole merger events. Others argue the signals are statistical artifacts, patterns in noise that look meaningful but aren't. The debate continues, but if the echoes are real, they would represent the first direct evidence of quantum effects at the event horizon, the place where quantum mechanics and gravity collide most dramatically.
In 1974, Stephen Hawking made a calculation that shocked the physics community. He combined quantum mechanics with general relativity near the event horizon and discovered something impossible. Black holes aren't entirely black. They emit radiation. The mechanism is subtle. Quantum fluctuations constantly create particle-antiparticle pairs throughout empty space. These virtual particles normally annihilate each other almost instantly. But near the event horizon, something remarkable happens. If a particle pair forms right at the boundary, one particle can fall into the black hole while the other escapes. To an outside observer, the black hole appears to emit radiation. This Hawking radiation has a temperature inversely proportional to the black hole's mass. For a solar mass black hole, the temperature is 60 nanokelvins, far colder than the cosmic microwave background. Such a black hole absorbs more energy than it radiates. But a black hole with the mass of a mountain would glow at room temperature. A black hole the mass of an asteroid would explode like a nuclear weapon. The implications are staggering. Black holes evaporate. Given enough time, far longer than the current age of the universe, even supermassive black holes will radiate away completely, leaving behind only faint photons scattered across an empty cosmos.
But this raised a profound problem that Hawking himself identified. The radiation appears to be purely thermal, completely random, carrying no information about what fell into the black hole. If a black hole evaporates completely, what happens to the information encoded in everything that crossed the event horizon? That information cannot simply vanish. Quantum mechanics forbids it. Yet, the mathematics suggested it does. This conflict, the black hole information paradox, has tormented physicists for 50 years. It represents a fundamental inconsistency between quantum mechanics and general relativity, two theories that work perfectly in their own domains, but cannot both be correct at the event horizon.
Perhaps the most spectacular evidence of black hole physics comes from relativistic jets, focused streams of particles and radiation that blast away from some supermassive black holes at speeds approaching that of light itself. The jet from M87's black hole extends for 5,000 light-years, visible in radio wavelengths as a coherent beam of energy punching through intergalactic space. The energy required to generate this jet is staggering, equivalent to millions of supernovae occurring simultaneously, sustained for millions of years. Scientists discovered the mechanism in the 1970s. The black hole's spin drags spacetime around with it, an effect called frame dragging. Magnetic field lines threading through the accretion disk get twisted by this rotating spacetime, creating a kind of cosmic particle accelerator. Particles trapped in these twisted fields get flung outward along the black hole's rotation axis at relativistic speeds. But here's the remarkable part. The energy powering these jets doesn't come from the matter falling in. It comes from the black hole's rotational energy itself, a mechanism predicted by Roger Penrose in 1969 called the Penrose process. The black hole is literally slowing its spin by converting rotational energy into the kinetic energy of escaping particles. Recent observations by the Chandra X-ray Observatory and the Very Large Array revealed something stunning. The jets show regular oscillations, wobbling like a spinning top. This precession occurs because the black hole's rotation axis is misaligned with the accretion disk. The jet's wobble maps the black hole's spin axis with precision, revealing rotation rates and orientations that tell us how these monsters formed and evolved. But this represents just one piece of a much larger puzzle hidden in the quantum realm.
In the 1990s, astronomers observing X-ray emissions from black hole accretion disks noticed something peculiar. The X-ray signatures showed iron atoms in the disk emitting photons at specific frequencies, but those frequencies were stretched, redshifted by the black hole's gravity. The most extreme observations came from stellar mass black holes in binary systems. Material in the innermost regions of the accretion disk, just 3 times the Schwarzschild radius from the event horizon, showed iron emission lines stretched by factors of 2 or more. These atoms were experiencing time dilation so severe that their clocks ran at half the rate of ours. Consider what this means. An observer hovering just above the event horizon would watch the universe outside speed up. Stars would be born and die in what seemed like moments. Galaxies would evolve and transform while subjective hours passed. The future would unfold at an accelerated pace. But for us, watching from outside, we would see that observers' time slow to a crawl. Signals from just above the event horizon would take longer and longer to reach us, red-shifted to lower and lower energies, until the observer appeared to freeze at the boundary, asymptotically approaching the horizon, but never quite crossing it from our perspective. This isn't just an optical illusion. Time genuinely flows at different rates depending on gravitational field strength. The event horizon represents the ultimate limit, the point where, from an outside perspective, time stops completely.